Okay, let's bring in again equations that we saw in the past. When we asked the same question about delta G and systems like chemical reactions, we said that the corrected form for delta G of an equation is delta G naught plus RT log of Q, where Q is, remember, the reaction quotient. Now, we have expressions now for delta G and for delta G naught in terms of the cell potential. So for the standard delta G, that would be minus NF times the standard potential. For the overall total real delta G, it would be minus NFE. So the first equation there on the left is the one we used in the previous unit on thermochemistry. The second and third equations here are the ones that we just looked at a few moments ago. Let's go ahead and substitute in the values for delta G and delta G naught. All right, the standards. And we get this equation here. Remember, we're trying to get to a place where we can describe the voltage of a cell where you are no longer in standard state conditions. In other words, you're no longer in 1 molar concentrations of the electrolytes, the solutions in the cells. Let's just algebra here, divide by minus NF. And what we're going to come up with is this expression here. This is a very important equation. It is called the Nernst equation. This is the equation that we use to calculate the actual voltage of a cell under non-standard conditions. Notice that mathematically, if you look at what's going on here, is we start with the standard potential and we're going to subtract an adjustment. Now, R is positive, T is positive, N is positive, F is positive. So what makes the potential be greater than or less than the standard is going to be the value of Q. So if Q is positive, if the log of Q is positive, then you're going to be having a decrease in the standard cell potential. But remember, Q is essentially products over reactants. So in other words, a positive Q means that you're getting more products than reactants. In other words, the reaction has advanced to the point where you are no longer in standard state, and so you are actually decreasing the voltage. That kind of makes sense. And I'll let you think about what's the other scenario. What would make log of Q negative so that when you subtract minus RTNF times log Q, you get an increase in the standard cell voltage. So once more, since many of these things are constants, at 25 degrees Celsius with 298 K, R, T, and F are constants, so we can simplify the Nernst equation to this format here. Or once more, if we prefer base 10 logarithms, we can use this one. Because a lot of the other equations that we use rely on the natural logarithm, I tend to typically go with this one here on the left. That's the one I typically use. But again, you're welcome to use the base 10 logarithm if it's easier to work that in your calculator. Okay, so let's do a little practice exercise here with the Nernst equation. Let's build now an electrochemical cell, or let's look at a reaction. But now what we're doing is, notice that we're going to react iron 2 with cadmium to produce iron and cadmium ions. But we have changed the concentrations of the electrolytes in here. Iron 2 is at 0.60 molar. Cadmium ions are at 0.010 molar. We can see from the form of the equation who is getting oxidized and who is getting reduced. So here we know that oxidation is, right, the cadmium. That's the guy who's getting oxidized here to cadmium ions. So that's the anode. Table says that the voltage for The reduction of cadmium ions is minus 0.40 volts. Don't forget, we don't change the sign at this point unless we decide to use the other approach to finding the final or total cell voltage. Reduction is iron 2 ions converting into iron, so that would be the cathode. 2 electrons are required for this. And again, looking it up on the table, we get the voltage for that, or the potential for that is minus 0.45 volts. In order to use the Nernst equation, we have to find out how many moles of electrons are being transferred. And we have 2 moles here, so N is going to be equal to 2. We also need the standard cell potential. So we're going to take the cathode minus the anode, so negative 0.45 minus negative 0.40, and that gives us a potential of negative 0.05. Okay, notice that this is negative, correct? So in the standard state, this reaction is not spontaneous, at least in the direction that it's written. Let's see if changing the concentrations of the electrolytes turns it into a spontaneous reaction. So that negative there, that is going to be our standard potential. So here we go. Here's the Nernst equation. E naught minus 0.0257 volts per whatever many moles of electrons are transferred, log of Q. So what is N equals 2. What is Q? Remember, products over reactants. In this case, we only consider those substances that are present as solutes in solution. So the solid iron and the solid cadmium, in other words, the electrodes themselves, are not going to be considered here. So we know that cadmium, the product, is 0.010 molar. Iron 2 ions, the reactant, is 0.60 molar. And you can see that ratio there is going to give you a value that's less than 1, which means the natural logarithm is going to be a negative number, which means that when you subtract the negative, it's going to turn positive. So let's put these numbers in. Again, I'm going to skip all the steps here, writing the equations on the calculator and stuff. And this is the result you get, 0.0026 volts. Notice that for this electrochemical cell, the voltage is actually positive. Not the standard one, but the actual voltage of this cell under these conditions of molarities of electrolytes, and therefore this reaction is spontaneous at 25 degrees under the conditions that are given here. Cool, huh? So the moral of the story is something similar to what happened when we were studying the second law of thermodynamics, delta G. We said that under standard conditions, a given reaction might not happen spontaneously because it has a positive delta G naught, right? A positive standard delta G. But under different concentrations and ratios of products and reactants, you might have a situation where the actual delta G under those conditions of concentrations and temperatures might be negative, and therefore you might be able to drive the reaction spontaneously. Similarly here, by adjusting the concentrations of your electrolytes, you can take a reaction that would be non-spontaneous in the standard state and turn it spontaneous under the conditions of the way you build this electrochemical cell or the way you carry the reaction. All right? Cool. Let's look at another application of this, which I find very interesting. It's something called a concentration cell. So in a concentration cell, what you do is you build a galvanic or voltaic cell, but the two half cells have the same material, just different ion concentrations. Let me give you a few moments to kind of download that and see if you understand what I'm saying. Actually, let me show you the cell diagram here. We learned last time how to read cell diagrams, right? Here we go. Again, don't forget, the double vertical bar in the middle represents the salt bridge, which is separating the anode on the left from the cathode on the right. The anode represents zinc being oxidized to zinc ions. The cathode represents zinc ions being reduced to zinc. The only difference is the concentrations in both of them. So let's look at the reactions. Remember that you read the cell diagram from left to right. So on the left side, we have oxidation. That would be zinc metal being converted into zinc ions and releasing 2 electrons. Don't forget, we have to put in the molarity because we are not under standard conditions here. The reduction, again, is on the right side. We read it from left to right. And in this case, zinc ions are being converted to zinc metal. When we add this, the electrons cancel out. But guess what? So does the zinc metal. See that? So the reaction you end up having here, net, is essentially zinc going from 1 molar to zinc going to 0.10 molar in ions. In other words, what we're seeing here essentially is simply a dilution. A dilution. I'm going to see if for Father's Day I can get me a new stylus here. This is essentially a dilution process. So a concentration cell, what it does basically is it causes a dilution of my electrolytes. All right, so let's write out the Nernst equation for this process. E naught minus 0.0257 volts. Remember, we have 2 electrons that are being transferred in this case. So that's the 2 there in the bottom. Log of, again, product over reactant. The product is essentially the diluted solution, and the reactant is essentially the more concentrated one. Now, in this case, in the standard state, right, there would be no transfer of electrons. If both of them were at 1 molar concentrations, both half cells would have the same thing going on. There's no net transfer of electrons. So E naught equals 0. And then the concentrations of my dilute versus concentrated zinc ions is 0.1 over 1. So that's a 1 in 10 dilution, essentially. So now it's just a matter of solving this, and essentially 0 minus all that. You can see where the log of 0.1 over 1, that number is less than 1. That means that you're going to have a negative log, which means that you're going to end up with this whole second term turning positive. Your final voltage now is 0.0296 volts. So this is very interesting. In other words, by simply building an electrochemical cell with different concentrations of electrolytes, I can actually generate useful power. I have a positive voltage. This is going to work. Electrons are going to be transferred, and I'm going to be able to produce energy out of this process. Okay, so here's what we're going to do. I'm going to walk you here before we close out through a couple of examples of where we see this in 2 scenarios. One of them is a biological scenario. The other one is a lab scenario. All right. So remember the concept. A concentration cell is an electrochemical cell where the only difference between the two half cells is the concentrations of the electrolytes. And by producing a dilution effect, for example, you can generate a positive voltage. Well, here's an example. In biochemistry, we study the process called oxidative phosphorylation. I think I mentioned this in our thermochemistry, our last lecture, where essentially chemical reactions are coupled with the formation or hydrolysis of a substance called ATP. And in that way, ATP serves as a currency of energy to transport energy from one place to another, either to capture the energy released by spontaneous reactions or to drive otherwise non-spontaneous reactions. A lot of the process happens inside the cell in an organelle called the mitochondrion, which is kind of like a bean-shaped, subcellular structure with a double membrane. The interior membrane of this thing is folded many ways to increase its surface area. And embedded in that membrane are a whole collection of enzymes and cofactors that participate in something called the electron transport chain. Between that inner membrane and the outer membrane, there is a fluid called the matrix, or in the intermembrane space, that has a particular function. So let's look at a cutout of that interior or inner membrane and all of the enzymes that are kind of inside of there, all right? So here is kind of like a cut through. Sorry, it's kind of like a sketchy thing here. So basically what you see here in the top is the outer membrane of the mitochondrion. It has the cytoplasm on one side and the intermembrane space on the other side. And then the bottom membrane, that's a lipid bilayer, has all of these factors and enzymes embedded in it. That's called the electron transport chain. So as, for example, a food item like glucose is getting metabolized, many of those processes represent oxidations, and therefore electrons are released. Those electrons are captured by different cofactors, NADH, FADH2, other things, and they are transferred along this chain. If you were to balance the redox equations for the processes that happen in these steps, what you'll see is that all of them are acid related and they release acid, in other words, they release protons. The mitochondrion is designed so that, as you can see here, the protons are released into the inner membrane space. That means that after a few rounds of this, you have essentially a high concentration of acidity in the intermembrane space compared to the lower concentration in the matrix of the mitochondrion, separated by a layer, which is the inner membrane. What do we call this? This concentration gradient, this concentration gap here, is essentially a concentration cell. You have higher concentration in the intermembrane space of protons than you do in the interior. The membrane channels are locked. They don't allow those protons to come across the membrane. So right now you have a potential because those protons want to move back in to equilibrate, to balance out the concentrations. The way that happens is through a very special enzyme called ATP synthase, which is embedded in the membrane and looks kind of like a motor that kind of like rotates around. So every time it rotates, it lets a proton in. And of course, that is in favor of an electrostatic attraction. In other words, it's driven to go there, which means this is a process that has a negative delta G. It releases useful energy, right? It releases useful energy. And what the ATP synthase enzyme does is it captures that energy in the form of ATP. Remember, our energy currency for the cell. So this is a biological example of the use of essentially a concentration cell. A gradient in protons between the two sides of that inner membrane creates a potential that can be used to generate useful energy, which is then trapped in the form of ATP molecules that serve as energy currency for other processes. Cool, huh? Here is another use of a concentration cell. I bet you've always been asking, how does a pH meter work? How come I stick that tube of glass in a solution and it reads the pH? Well, this is actually an interesting phenomenon here. The reaction by which this was first developed was actually developed in the early, I want to say 1900s by Fritz Haber, the famous German chemist. And then later on, it was developed by Beckmann by coupling it with, an electronic instrument that could amplify the signals and give us a readout of pH. So this is the probe, the bottom of the pH electrode. Notice that there's two electrodes in here. Number 1 points to the reference electrode. Number 3 probes to the measuring electrode. These two electrodes are actually separate from each other. They do not come in contact. Each of them is submerged in an electrolyte solution, typically of KCl at pH 7. But they're separate from each other, all right? Now, the outside of the bulb is made of a special glass that is coated by different materials, sometimes some kind of a hydrated gel. This is actually the portion of your electrode bulb that goes into the solution. Notice that the electrodes themselves are typically made of like a silver related thing, just to make it very stable. So how does this read pH? Well, it doesn't. It doesn't really read pH. What the electrode does is it detects a potential difference between the solution that you're putting it in and the measuring solution that's surrounding the measuring electrode. This is item number 5 here on this picture. So let's say I submerge this in a solution that has a concentration of hydrogen ions different than 10 to the minus 7 molar, which is the pH 7 solution that you have inside. Well, what will happen is on the surface of the glass, these ions are going to start exchanging with the surface of the glass. This triggers a potential across the glass that causes ions on the inside to also relocate themselves. Once you start changing the profile of ions in that interior solution, that electrode, item number 3, detects that change. And because it is measured against the reference electrode, number 1, and these are connected not to each other, but through a circuit in the detecting mechanism of the machine, that detecting mechanism registers a voltage difference. It's essentially a voltage difference ultimately between the solution where the measuring electrode is and the solution on the outside, the one that you're trying to test. And of course, what you have in the machine is you have a programming system that converts that voltage difference into a pH reading, either analog in the form of a needle over a display or an actual digital display. And that's how a pH electrode works. Of course, guys, there's all kinds of other bells and whistles in here, all the kind of things you can tweak. I'm just giving you like a very sketchy description of how this works. The point is that essentially a pH electrode is a probe that registers an electrochemical potential between two solutions that have different concentrations of solutes in them, specifically hydrogen ions. All right.